1.6 exponents and square roots. We got our three objectives there. So I know what a base, exponent, and square root represent. I can evaluate expressions with exponents, and I can evaluate simple square roots. I'm putting simple up there because we're not going to give you anything that I guess we couldn't do with just regular multiplication on that. So no simplification of square roots, no funky looking stuff. But there is a little bit of memorization involved. But it'll take us back to the multiplication table. We're going to see this a few times because, especially with exponents and even square roots to an extent, they represent something that we can change the way it looks, which hopefully will be something that will help us understand them a little bit better. So on the surface, if we look at exponents, it's like, what the crap is that little number in the top right corner of that number? If you understand multiplication better, then you are welcome to change it into multiplication. But we'll see. Okay, so this is part of one of our objectives in 1.6. But what we really need is to be able to know the language here, right? Like we talked about, mathematics is sometimes its own language, and so we have some math hieroglyphs, I guess. Maybe I'm not using the right word there either. But in this case, you have a base, and the 5 there is what we call a base. And then the 4 is a smaller number in the upper right-hand corner of the base number. So this would read 5 to the power of 4. Okay. Now again, even just knowing how to read it, well, what does it mean, 5 to the power of 4? A base and an exponent, okay? So on that last slide, we were looking at 5 to the power of 4. Well, the base tells us the number that is being repeatedly multiplied by itself. So this would be 5 times itself. The exponent tells you how many times to multiply it by itself. So it is different than direct multiplication. This does not read 5 times 4. It is not 5 groups of 4. Because that would be addition. This is 5 multiplied by itself 4 times, and if you wanted to, not that I'm thinking that you would want to, but if you wanted to, you could actually change this into its expanded multiplication, repeated multiplication form. 1, 2, 3, 4. So those 4 5s are being multiplied, so there's my multiplication symbols. That's okay, right? Now, why would you want that? Well, math people want it because we're pretty lazy, and we don't like writing 4 5s like that. We say it's easier to just write a 5 and a 4 like this, in this way, to communicate to people that this 5 is being multiplied by itself 4 times. So down here as well, 6 to the power of 4, you could say, well, that's 6 multiplied by itself 4 times 2. That's TOO2. Or this one. This is repeated multiplication. 7 times 7 times 7 times 7 times 7. That would be a base 7 to an exponent of 5, or power of 5. But again, do you want to write it like this? I don't know. Maybe that would help you. Maybe it would help you to write it like an exponent. It depends on the scenario. When we get into at least fractions, if not the division stuff, this tends to help us when we start making what we're going to call phantom ones, which is coming. First, let us simplify. We'll start with this top one. Now, just if we were to read this, that would be 5. In fact, I'll put 5. 5 to the power of 2. Okay? 5 is our base. 2 is the exponent. Now, it's saying to simplify, and what does that mean? Well, it means that we want what this would be without an exponent, but without multiplication either. Now, it may help us to see this as the base multiplied by itself, in this case, 2 times, right? So in this case, we got 5 times 5, which if we go back to our multiplication table would be 25. Okay, now again, please do not mistake this for 5 times 2. I know I kind of wrote that kind of funky because of the blank right there, but it's 5 times 5, which is 25, not 5 times 2, which would be 10. That would be incorrect. This next one, 6 to the power of 3, let's put that on there too. So 6 to the power of 3. You can say base 6 with an exponent of 3. It's the same thing. Base 6, exponent of 3. So how many times is the 6 being multiplied by itself? I will rewrite this as repeated multiplication, which hopefully will help us to actually solve this. 6 times 6 times 6. So there's our multiplication symbols. Okay. I can't do that all in my head. And if you can, that's pretty freaking awesome. But for me, I'm going to start with just the first 6 times 6. I'm going to show my work. You know what? I'll show it over here. I just need more space right there. Okay, now 6 times 6, that's one of our multiplication tables. 6 groups of 6 is the same as 36. But then I have to multiply by this 6 as well, so that's still multiplied by 6. And that's the part I would want to show some work with. Okay, so let's stack and multiply this. 36 times the 6 right there. And let's see what this is. So, well, in the ones place value, 6 times 6, again, would be 36. And that's great. But the 3 tens I will move over into the tens place value, knowing that I need to add those to whatever the product of is between 6 and it's really 30, right? So 6 times 30 there would be 18. But then I would have to add the 3 that we already had carried over. 18 plus 3, 18, 19, 20, 21. So the product of 6 times 6 times 6 ends up being 216. But here's a common answer from this bottom one, 1 to the power of 7. Common answer for this one, at least on previous tests or quizzes, would be 7 right here. Okay. Now the answer is not 7. 7 would be incorrect, and here's why. So that's 1 to the power of 7, which means that it's really 1 times 1 times 1 times 1 times 1 times 1 times 1. Sorry about the redundancy, but that's what exponents give us right there. And I think that's 7, yeah. Now, if it was addition, that would in fact be 7 right there. But it's all multiplication. And if we go back, not even too far, but anything times itself is, anything times 1, that's what I meant. Any times 1 is itself, that's better. I know I'm exposing how bad I am at typing, but I don't care, because I'm a math nerd. Nothing like that bothers me anymore. So anything times 1 itself, including 1, by the way. So 1 times 1 would be 1. It's like one group of 1, it's still 1. And then another group of 1, still 1. Sorry, 1. And then another 1 times 1 is 1, times 1 is 1, times 1 is 1, times 1 is 1. And so the final answer here is just 1. Let's take this to the extreme, all right? Now, I'm not going to, in fact, I'll do it underneath, so let's give ourselves some space here. What you've just seen, 1 to the power of 7, let's change that just a little bit. Let's make that 1 to the power of, you guys give me a couple numbers. Now, that seems kind of large for an exponent, but this is just 1 times itself 48 times, right? So let's put that, this is 1 times itself 48 times, okay? It's not adding to itself 48 times, it's just multiplied by itself 48 times. But the thing is, anything times 1 is itself, including 1, which means that this, if we were to solve for it, or evaluate it, would be, that would just be a 1. And in fact, it wouldn't matter how big this number is, the answer, still 1. Okay? All right, all we want for this is for you to look at these and say, yes, I can change this into exponential form. So this first one, 50 times 50 times 50, let's look at it like this with the vocabulary, okay? We have a base, it's repeated multiplication, so we should have an exponent. What would my base be on this? 50, yep. Very good. So 50 is our base because it's being repeatedly multiplied by itself. And there's 1, 2, 3 of them. So it is 3. Okay, so that would read 50 to the power of 3. And the way I have it color-coded makes that a little bit easier. Here's what we would not want on like an exam or some kind of written assignment, right? Is this is 50 to the power of 3. Okay, because grading that, I look at that like 503. Okay, the exponent it's purposefully supposed to be a little bit smaller, at least a little, like half as big, as the base values and in the upper right-hand corner. This doesn't look very, I'm just giving you an example of stuff that we've seen in the past. Or, you know, even something like this, like, oh, okay, I mean, I can see that 3 is raised a little bit, so just try to make it a little bit smaller at least. But having raised it, yeah, that's okay. It's just not great. All right, this next one, you know, here we have 10 times 10 times 5 times 5 times 5. It's repeated multiplication, but there's 2 different values that are repeatedly multiplied. This tells us then that we're actually going to have 2 bases. Okay, so I've got a 10 base right here. So I've got a base 10, and it's being multiplied by itself 2 times. So that's going to be 10 to the power of 2. But in addition to that, we also have base 5, because it's being repeatedly multiplied by itself 3 times. So that's multiplied by 5 to the power of 3. Just to clarify that it is multiplication, I'm going to put it in there. And that's good right there, okay? So roots, we're just looking at square roots, by the way, which is, I like square roots, which I'm kind of reluctant to say out loud because I don't think it makes people happy very much. But I like them, okay? This is our symbol for square roots here. Another way, this symbol right here can be called a radical. Not like Saul Alinsky, but just, you know, a math radical anyways. So square root, this would be a square root. There's other roots. You can have cube roots or fourth roots or fifth roots, but we're just concerned with square roots. So we see here a square root is called a square root because it is specifically related to squares. And the unique thing about squares, here, let's take a look at a square. I can use some technology to help me draw this. That is supposed to be a perfect square according to my technology. We'll pretend like it is anyways. Okay, so what do you guys know about squares? There we go. They are the same on all sides. And that is the important part. So side lengths we generally show with the letter S. And if you were to find, and we haven't gone over this yet, but if you were to find the area of a square, you would do the side length, and this is where it gets tricky because students are waiting for me to put that second S there. But this is a family-friendly video, so I'm going to put to the power of 2. Now, area is the side length to the power of 2. Asking for a square root is like starting with an area of a square, but asking what the side length is. Okay, so this one right here reads, this is the square root of 100. But it's really asking what number times itself is 100, because that's how you find the area of a square. So we're saying you start with the area of a square of 100. What number multiplied by itself is 100? Of course, the chart kind of gives us that information right there. From what I remember, I think there's only one 100 on here. Found it. And so we would trace this back to 10 and 10. Okay, so what number times itself is 100? Boom, it's 10. On our multiplication table, which, you know, we hope will be memorized fairly soon, these numbers, any number multiplied by itself would be considered what we call a perfect square. It goes along this diagonal. I'm trying to make this look good. That's okay. Okay, so if I took any of these, then you could find an actual number, whole number, multiplied by itself to get that value. For example, 49 would be 7 times 7. Or 144 would be 12. Didn't go along that row very well, but 12 times 12. Okay, and if we ask these numbers, which is all we're going to ask today, then you should be able to figure out some of these numbers, even if you just need to look at the table. You can look along that diagonal still, but let's look at the real question. This would read the square root. That's how it reads, the square root of 16. But it's really asking what number times itself is 16, question mark. Okay, so the number that multiplies by itself to get 16 is 4. Now, 4 times 4 is 16, but the square root of 16 is really asking for one of those side lengths of a square, and so this one is just an individual 4 by itself. Okay, so the number multiplied by itself to get 49 is 7. This one's a little tricky because it's not on our chart, right? So this may take a little bit more thought on our behalf. It can't be 12 times 12 because that's not big enough, or that 12 times 12 is 144, which is not big enough. So what is it going to be? Here's essentially what we have to do right now, because we don't have anything memorized beyond 12. We have to kind of do some guess and test on this. So I'm going to do 14 times 14, right? We're just guessing. And then let's see if it works. Okay, so is 14 times 14 169? Well, 4 times 4 is 16. And technically that's enough. I'll finish the work here, but we'll carry the 1 over. 4 times 1 would be 4, but adding the 1 is 5. I apologize for going through this quickly. Now in the tens place value, 1 times 4 is 4, and 1 times 1 is 1. That would be 196. It's close. It almost looks the same. It's just not exactly the same. So 14 is too big. Bam. So 13. Let's try 13, see what happens. 13 times 13. 3 times 3 is 9. 3 times 1 is 3. Now the tens place value, 1 times 3 is 3. 1 times 1 is 1. When we add this, we get 169. So now we can see what the product is between 13 and 13. It's the same value multiplied by itself. So it's just an individual 13 as our answer. So, I mean, if you wanted to, you could add this at the row of 13 right here, at least in the corner, and get 169, or I guess add the 196 too, get the next one.